Hey, my name is Fisher, and today I'm going to be teaching you about related rates. Related rates are defined as a means to find the instantaneous rate of change at any point in an equation at any point in time. Related rates use derivatives, and we know that by definition of the derivative that is how you can find the instantaneous rate of change of a function. Related rates are always in the form of word problems, so if you have any anxiety about word problems, you need to get over it. There are a few basic steps to solving problems involving related rates. First, you need to identify the equations you'll need. This involves geometric solids, area and volume, and Pythagorean theorem. These next two steps aren't necessary, but they are helpful. You can list the values that you need to know and the values that you already know. And drawing a picture can help you visualize what you need to solve. These two steps basically just help you graphically visualize your thoughts and help you solve the equation. And finally, you will need to differentiate. I've made a note over here. Values after differentiation will always be with respect to time. These will be represented as dx over dt or dy over dt, something like that, which basically means the change in x over the change in time or the change in y over the change in time. All right, now let's start off with an easy example. A metal disc expands when heated. The radius of the disc expands at a rate of 2 inches per minute. Find the rate of change in area when the radius of the disc is 9 inches. All right, our first step, identify an equation. Here we're going to need the area of a circle. Area equals pi r squared. Now what we're going to do is make a table of values that we know and what we don't know. We're looking for the change in area, so that will be dA over dt, which we do not know at the moment. We know the radius, which is 9 inches. R equals 9. And we know the rate of change of the radius, 2 inches per minute. So our dr over dt equals 2. And now we will, since we do not need to draw a picture, we can now differentiate. Using the power rule, dA over dt is equal to 2 pi r, and since we differentiated, it'll be dr over dt. And from here, we can sub in our known values and solve. dA over dt equals 2 pi times the radius, which is 9, times the rate of change of the radius, which is 2. So here we have 2 pi times 18, or 36 pi. So now we know that the area is changing at a rate of 36 pi square inches per minute. As I showed you in part 1, I taught you the basic steps for solving a problem using related rates. In this one, however, it'll involve a special step that I'll point out to you when we get to it. The problem is a conical cup 3 inches across the top and 4 inches deep is full of water. The cup springs a leak at the bottom and loses water at a rate of 2 cubic inches per minute. How fast is the water level dropping at the instant when the water is exactly 3 inches deep? Okay, so it's kind of an open-ended question. What I've done is I've drawn a diagram of what we're dealing with in the problem. It's 3 inches across the top and 4 inches deep. Also in part 1, I told you that a very helpful step is making a list of the values that you know and what you're trying to solve. All right, start off with H. So we know that the water, or we're trying to find it when the water is 3 inches deep. So our height will be 3. It is asking how quickly the water level is dropping. That will be our change in height, or our dH dt. This will be what we are trying to solve. And our change in volume is negative 2 cubic inches per minute. It will be negative because the cup is losing water. So our dV dt will be negative 2. Also in part 1, I told you about you need to know your formulas before you start it. For this problem, we're going to need our formula for the volume of a cone, which is pi over 3 times the radius squared times the height. Normally here, I would differentiate and then plug in for values, but here's the problem. There's no r or dr dt up here. So what we're going to have to do is find a way to express r as a value of h. So what we're going to do is take the original measurements of the cup. The diameter is 3, therefore the radius is 3 over 2, and the height is 4. Now, I'm going to set these up as proportions. So r over 3 halves is equal to h over 4. And cross multiply, 4r equals 3 halves h. Divide by 4 to get r by itself. R is equal to 3/8 h. Now that we have r as valued h, we can put this into our volume equation and have a formula for the volume that only uses one variable. So we have pi over 3 times 3/8 h squared times h. Now, we're going to use our algebra to clean this formula up a little bit. And we're just going to multiply these values back in. 9 pi over 192 h cubed. Now, this is our simplified volume formula using only h. Now, from here, we can differentiate. Volume is equal to 9 pi over 192 h cubed. Actually, we should simplify this. This should be volume is equal to 3 pi over 64 h cubed. Now we can differentiate using the power rule. 3 times 3 is 9, dv over dt equals 9 pi over 64 h squared. And don't forget your dh dt because we differentiated. dh dt. Now we have our dv dt and we have our h. So now, since these are just numbers, we can solve for our dh dt. So negative 2 is equal to 9 pi over 64 times 3 squared times dh dt. Now, we can multiply 3 squared into this fraction. So negative 2 is equal to 81 pi over 64 dh dt. Now, we learned in algebra that when you divide, you multiply by the reciprocal. So, we have negative 128 over 81 pi is equal to dh dt. And here's our answer. So basically, this conical cup is losing negative 128 over 81 pi cubic inches per minute. This is basically losing 0.5 cubic inches per minute. A ladder 13 feet long is leaning against the side of a building. If the ladder is pulled away from the building at a constant rate of 8 inches per second, how fast is the area of the triangle formed by the ladder and the walls changing when the top of the ladder is 12 feet above the ground? Okay, so here's what we're going to do to start. I first realized that these units are in feet and these are inches. So I converted all the units that were in feet to inches. Like the height of the ladder, which is 144 inches, and the actual length of the ladder. This is just the height off the ground. This is the length of the ladder is 156 inches. I used Pythagorean theorem to find the length of the base, which is 60 inches. I also used the Pythagorean theorem along with related rates to find the rate of change of the height, which at 60 is being pulled away, is losing 10/3 inches per second, which is about the 3.3 feet. Now, I'm going to make a list of the values we know and the values we're trying to find. The area of the triangle, dAdt, we do not know this, we are trying to find it. We know the height off the ground, 144. We know how fast the height is changing. It's losing 10/3 inches per second. We know the length of the base. The base is 60. And we know how fast the base is changing from the problem. You can see it's being pulled away 8 inches per second. Now, we also need to know the area of a triangle. The area is equal to 1/2 base times the height. Now, we will differentiate this using the product rule. dA over dt equals 1/2 the first base times the derivative of the height, dh dt, plus the second height times the derivative of the first, db dt. Now, we're going to plug in the values we know. Now, our handy dandy little calculator will help us get to where we need to be in. All of this right here comes out to be 952. Now we multiply 952 by 1/2. Be 476. What we can conclude from this is that the area of the triangle, when the ladder is 12 feet above the ground, is gaining 476 square inches, or about 39.6 square feet.